Okay, guys, let's start the last session of the workshop. So it's my great pleasure to welcome Vivek Sarkar from Rice University. Vivek is well known for his contributions to compilers, language runtimes, program analysis, concurrency. He got his PhD from Stanford University, and then he spent, I guess, quite a bit of time at IBM Research in Watson, and where he led essentially the entire research area in programming languages, programming tools. Many important projects started there. The X10 programming languages, the X10 programming language, the JAX RVM, and various other projects. And then after some time there, he moved to Rice University, where he's now a full professor and also the department chair. So go ahead.
Thank you, Martin. So one of the things that was a lot of fun in those days at IBM was recruiting good PhD students as interns. So Martin Vechev was one of them. And also getting distinguished visitors. So I remember Patrick and Radia visited us for a year, and that was good. Okay, so today I want to talk about parallel programs, structured parallel programs, and acknowledging the group at Rice. We have a lot of fun working together. I don't have a recruiting slide, but if you're interested in collaborations or postdocs or anything, feel free to talk to me. And a number of people, including some senior people who retired from IBM and Intel, are working also as part-time senior research scientists. So we have a good time together. So here's the thing. You all know that all computers are parallel computers. When I did my PhD, we really had to fight to get access to a parallel computer. Now I teach a second-year undergraduate class on parallel programming taken by 90 to 100 students. Everyone has a parallel computer in the classroom already. They have 4 cores. They also have smartphones, which are multi-core. And of course, with cloud computing, there's lots of parallelism everywhere. So this is very exciting for us, people who do research in parallel computing. But what it also means is that effectively, any application today is also parallel by default. It may have components. Some components may not be aware of parallelism, but that's slowly starting to change. So I kind of see it as analogous to how object-oriented programming came about. You know, it took a while for it to catch on, and it was really misused and abused in the early years till people figured out how to do it systematically. I think parallel computing is in the same transition right now. And so because this the programs are parallel by default, there are new challenges for the theme of this workshop: software correctness and reliability. And today I want to focus on 3 aspects, which are avoidance, detection, and repair. And so the context is this Habanero project at Rice, where we do research across programming languages, compilers, and runtime systems, and use different kinds of parallel applications and different kinds of hardware as sort of the boundary conditions for our research. The research in languages, compilers, and runtimes are all tied together in a very closely coupled way by one unified execution model that I'll talk about, and that's what we refer to as structured parallelism. And then we have implementations of these execution models, either in some more declarative languages, DSL-like, the concurrent collections. There's a data flow graph language also. And we have some mid-level programming models where these primitives have been added to C, C++, Java, and Scala. And so, for example, in the sophomore class that I teach at Rice, we have Habanero Java, which adds these constructs to Java 8 with Lambda interfaces. So generally, we feel that the structured parallelism, which I'll define in more detail, helps at many, many levels. We believe that programming, so when you ask someone what's an explicitly parallel program today, right now it's a mix of the semantics of what can run in parallel and also the mapping onto a particular hardware. So the choice of parallelism might be different for a GPU or a CPU or a message passing cluster. Whereas we are trying to take the approach that the programming model should specify everything that can run in parallel, not how it should be exploited. So that's a logical parallelism. And the structured primitives help provide the strong semantic guarantees that I'll talk about. It also helps that compilers can then analyze these programs, because today very often the parallel primitives just get compiled into some kind of APIs, whereas we need them to be first-class primitives in the compiler intermediate representation. So that needs extensions to the foundations of compiler theory. So for example, we have some recent work on extending the polyhedral framework for the case when the input program is a parallel program instead of a sequential program. Runtime systems need to be able to implement these primitives efficiently, and we've shown that these structured primitives can actually lead to more efficient and scalable runtimes than the unstructured ones. And now coming to the theme of this workshop, debugging and verification tools should be sound and complete to the largest extent possible. And we believe that these structured abstractions can help programmers avoid, detect, and repair bugs more effectively. So what are these primitives? These are the ones that they have, and you can think of them either as primitives that can be used directly as a programming model, or they can be targeted by some higher level abstraction, like a domain-specific language. So for the computation and data transfer, we have a basic idea that everything should be an asynchronous building block. So we have asynchronous tasks, futures, data-driven tasks. Termination is the synchronization that occurs upon a task termination. I'll tell you about the finish construct, the future gets. A wait is something that's like event-driven task. It triggers other tasks that could be waiting for the termination. And then there are data transfers, which are getting increasingly important in future hardware, where data movement is a key limit. So not only do you have to coordinate the parallelism in the computation, you have to coordinate data movement, which can be up and down the memory hierarchy. It can be communication. It could be even data transfers to an accelerator like a GPU. So this is a combination of primitives over there. I won't be talking much about this area because this is really locality control. It's a separation of concern. Given the logical parallelism, how do you actually guide the mapping on a particular hardware? Hierarchical places give some affinity, and the global namespaces help with the distribution. But there are cases where the tasks need to synchronize with each other, not only upon termination, but while they're running. And there are two kinds of synchronization there. There's mutual exclusion, which is typically used for non-deterministic concurrency. And there we have an isolated construct that's analogous to the atomic construct you might have seen in transactional memory model. And we've also integrated actors in this model and actually come up with some extensions to the actor model. And then there are collective and point-to-point synchronizations. The phasers include barriers and point-to-point semaphores and accumulators. So it may seem a little ad hoc that I put the list, but there's a context behind them, and if you're interested in any of these, I can point you to specific papers over there. The key thing is they can all be composed and used together. So it's not like you write your program only in the actor model or only in the task model. You can combine them completely. So now let me get to some of the benefits you get from having the structure. I'll just give a very quick summary, and then we'll go into some of these properties in more detail. You can actually classify programs based on the subsets of primitives that they use. So I'm going to right now refer to a few properties. Deadlock-free means you guarantee that the program will not deadlock. Data race-free. Determinism, actually, there are two aspects of determinism that we worked with. Structural and functional. Functional is what you would normally expect. For a given input, you always get the same output. Structural is for a given input, you always have the same dynamic structure of the computation, what we call the computation graph. And then there's a property that data race freedom implies both structural and functional determinism. The structural determinism is very powerful for debugging because when you replay a program, it's always the same interaction graph. So this shows the important role that data race freedom plays, not just by itself, but for a subset of programs. And serial elision is the property, which I'll state very informally, that you can transform a parallel program to a sequential program by removing the parallel constructs. And programs that satisfy the serial elision properties are those where the resulting sequential program is consistent with the parallel semantics. And it turns out that you can now have a Venn diagram based on these properties. There's this sort of the serial elision set. So if you use certain constructs like async, finish, task creation, termination, and future, where the future references are final, then it is guaranteed to satisfy the serial elision property. Serial elision, by the way, also implies deadlock freedom, because if you get a sequential program, then you know that's one deadlock-free execution of the program. So you have that, and you have the data race freedom implying determinism. If you add more generality, you add barriers and phasers, you have to drop the serial elision property, it turns out. And if you add even more generality with event-driven or data-driven tasks as async await, you have to drop the deadlock freedom property, because there, well, it may not technically be thought of as deadlock, but you could have some tasks whose preconditions are never met, so they never get to execute. So it's kind of like a task that was blocked right at the start. So this is great, because you get these guarantees just by looking at the primitives. So to prove the guarantee, if all you have, it's sufficient for some programs to just prove it's in the appropriate subset. Okay, so now what I'd like to do in the rest of the talk is sort of give you examples of avoidance detection and repair. So in the avoidance case, let's pick deadlock avoidance. And the goal, of course, is to use these structured primitives to get sufficient conditions so that you know you're guaranteed that you'll never encounter, in this case, deadlock in any execution of the program for any input. And so this is not something you can take for granted in general. It's very easy in thread-based programming or any other programming model today, for that matter, to create a deadlock. Here's one with Java threads. I just made these static fields for convenience. They could be fields in a dynamic object. And you, in part because the creation and the starting of the thread are separate, there's no data race over here, but you'll still have a deadlock. And this is using the Java 8 Lambda notation. So all thread 1 is going to do is join on thread 2, and thread 2 is going to join on thread 1. You start both the threads, you'll have a deadlock. Very, very classic and simple example. However, if you have a structured fork join parallelism, like we do in async finish, or it would also apply to silk spawn sync, you can never get even though there's a blocking operation. So let me explain the finish construct briefly. This originated from our work on the extend language. So you could have async statements that are spawn tasks, and a finish scope says that you need to wait for all the tasks that are spawned in that scope before you can go past the end of the finish. So in a way, the end of the finish is like a join, but it's a structured join. You don't get to pick which task to wait on. It's block structured. And actually, in general, we see a high-level analogy, or at least we are inspired by all the work from decades ago when our leaders in verification in the computer science community advocated for structured programming, to say it's easier to verify structured programs than unstructured programs. We believe that the same thing will happen in parallel programs. And these can be arbitrarily nested. So an async over here runs in parallel with this whole finish block. The try-catch also shows that we have a sound exception semantics. You can get multiple exceptions, collect them in the finish. And the reason why you cannot have deadlock is because when you think of the dynamic structured tree as the program executes, there's a nesting of finish and asyncs, and the wait for relations always go upwards in the tree. So you can never create a cycle. So that's the intuition as to why you cannot have a deadlock. So here's another construct, barriers, which are really well known for all kinds of deadlock situations in different programming models, certainly for MPI. I've included an example from OpenMP. So here you have a parallel region, which is entered by some number of OpenMP threads. Let's assume there are at least 2 threads. And what we're going to do is say that all threads participate in the barrier except the thread with ID equal 1. So if the thread ID is not equal to 1, you do a barrier, otherwise you skip to the end. And actually, the program does not conform to the OpenMP spec, but that doesn't help the programmer because it just says it doesn't conform. What behavior they'll see depends on the implementation. On some platforms, implementation, they may get a deadlock. Sometimes it might just complete silently. Sometimes it might result in something else that's undefined. And you can create similar models. So our approach to structure parallelism to deal with these kinds of synchronization relates to the work we did on this construct called phasors, which might take a little more time to explain. So this is a generalization of barriers and also point-to-point synchronization. And the idea is, in general, you can allocate these synchronization objects called phasors. And every task, when it's created, can be registered on multiple phasors in certain modes, which could be signal, weight, and you can see a lattice structure here, signal weight, that lattice structure is based on the capability. Signal weight is the combination of two. And single is a special case of signal weight where during the barrier transition, you do a certain operation just once. So there's some properties that you need for soundness over here. So for instance, when you create a child task, its capabilities should be a subset of the parents. So you can't have a parent that only has a signal capability on a phasor and then have it create a child that also waits on the phasor. And also a key thing is that when a task ends, it implicitly drops all the phasor registrations. So then the barrier operation that we call next, which is, and this is also derived from the early work on extend clocks, if you're familiar with that, is that when you say next, you advance each phasor that the activity is registered to the next phase. And what in advance means depends on the registration mode, signal or wait or both. So you actually have deadlock avoidance with phasors. I've shown a simple example, but somewhat contrived example here where you have an original task, it's created 2 child tasks, and then immediately after that it does these statements. And I've textually aligned the barriers. So you can see that the first task will do statement 1, the second task will do statement 4, the parent task will do statement 6. They will all do a barrier, but that means they're all registered in signal wait mode, which is the default. And then before going to the next phase, they'll wait till all 3 reach that point, then go and do statement 2, statement 5, statement 7. And now this task A3 is going to do something like what we saw in the OpenMP example. It's just going to end. It's not going to do a barrier. And because the semantics is that you drop the registrations at that point, there's no problem. The termination effectively serves as a notification that it's no longer participating in the barrier, and so there's no deadlock. And you also have dynamic parallelism. You can have new tasks join the phasors. You can have them tasks leave, and this guarantees that property. And this can even be extended. So this is similar to what's there in extend clocks. But one extension we have with the individual modes is that you can also have point-to-point synchronization. So here I'm showing a really simplified version of some iterative solver for something like a partial differential equation where your a sub I is being updated as some function of b sub I minus 1, b sub I plus 1. And then you do a barrier because before you go to you're going to update b sub I, and you want to make sure that everyone has completed the reads in line 5 before they go to the next iteration. So basically what you have is you have n tasks, and each of them is doing this while loop. But because we want convergence, we want to allow some iteration to, if they've detected convergence for their element, just to break out of the while loop, while others could keep going on. Now, depending on function f, it's possible that some might converge earlier and some others might converge later. And this works just fine also because exiting from the while loop terminates that particular async, and it automatically deregisters. Now we have an array of phasors, so each task is registered on ph sub I in signal mode, and ph sub I minus 1 and I plus 1 in wait. The next takes care of the semantics to say signal this phasor and wait for the 2 others. So, and also there's a postdoc in my group who's formalizing all these deadlock avoidance proofs using the Koch theorem prover, so if you're interested in that, he'd be very happy. He's uploaded it all to GitHub somewhere to share it with you. Now, there still can be deadlocks, and futures are a really important structured parallel programming construct. They really capture functional parallelism. But it turns out that if future references participate in a data race, then you can build an example a little bit like the original example I showed you with Java threads. So here what we have is we have two fields, F1, F2. They're both initialized to null. And then we create two future references, F1 equals async, F2 equals async. And the way futures work is you have the future reference, and then you do a get operation. And the get operation will either return the value from that was produced by the task, or if that task has not completed, it will wait until the task is available. And here what we're doing is some really messy code with data races where the future for F1, that body A1, is going to iterate on the F2 field till it becomes non-null and wait on that. And the future for F2 is going to iterate on the F1 field and then do a get on that. And so you've created a deadlock cycle. But the only reason this could come about is because there's a data race. So that's why in my earlier Venn diagram I mentioned futures with final. So one sufficient condition to guarantee deadlock avoidance with futures is by avoiding data races on future references. And if they're final, that's one way you can guarantee there won't be data races. So you see how all these properties come together. So that just gives you some idea about avoidance, that you have this whole space, and then with different sufficient conditions, you can guarantee different things. I didn't talk about it, but there are certain subsets that guarantee data race freedom. If all your shared accesses are the results of return values of futures, or internal state to an actor, or within some isolated, then also you can guarantee data race avoidance, for example. So let's talk about bug detection. So there are still bugs for some of the reasons that I mentioned that it may not be possible that you can guarantee them to be avoided, even though you have these rules. Programmers, for data race is the classic one. Programmers may not, for many reasons, be willing to live by the restrictions that I mentioned, that all shared data must be future return values on actors and so on. They may have other reasons to say, well, I have other forms of shared data and I can use other synchronization to guarantee there's no data race, but then the burden falls on them and they can have bugs and so on. So if there's no static guarantee for avoidance, then we need to help the programmers with detecting the bugs. And the focus of our work in this area has been more on dynamic bug detection so that we get both the soundness and the precision. But we definitely leverage static analysis for efficiency over there. And there are many examples, and I'll see how much time I have, such as data race detection, permission violation, commutativity violation. These are examples where it's not easy in general to guarantee avoidance, so you need the detection. So data races, there can be many definitions. I think I'm using a pretty standard one to say that if there are two accesses to a shared memory location, where at least one of them is a write, and here I'm also saying the program structure imposes no happens before ordering. So sometimes people refer to this as the potential data race, because the whole program could be running on one processor core, and we'll still say there's a data race here and here, because it's not actual that they actually had to run in parallel. So we had some work in PLDI 2012, and this was also with Martin and Eran, where we worked on a dynamic data race detection algorithm using the structure called the dynamic program structure tree, and really leveraging the structured parallelism to get an effective solution. So the dynamic program structure tree is similar to what I'd shown you earlier when I introduced async and finish. It maintains the dynamic parent-child relationships of the async and finish constructs. And the leaf nodes are the actual computations, the steps. And within a step, there's going to be no async or finish. And also, this is an ordered tree where the children of each node are ordered from left to right. So here's an example where you have some nested finish and async, and you can see that at each level the children are ordered, and the computations only occur at the leaves. So there's some interesting properties that follow from structured parallelism. So for a given input, and this is certainly not true for schedules, but it's true for the tree, you'd always get the same dynamic program structure tree if no data race is detected. And this follows from the structural determinism that I mentioned. For the same input, it doesn't matter which asyncs are executed in which order. If you don't have a data race, the final tree will be the same. The tree will kind of grow downwards in different ways in parallel, but the final value will be the same. So that's very helpful for debugging. Also, the path from a leaf to the root stays invariant as the tree goes. So if you reach any step node, then its path to the root will always be the same, even though the rest of the tree is still growing in parallel. So that also helps for doing this data race detection in parallel. And as I mentioned earlier, the computations happen in the leaves. So then, dynamically, to identify which accesses may happen in parallel, that is, are not ordered by happens before edges, at least for these constructs, async and finish, it's a very simple algorithm based on, you take the two accesses, S and S prime, and let's assume S is to the left of S prime, according to the left to right ordering in the tree. Then you find the least common ancestor, you find the child that is the ancestor of the left access S. If it's an async, then you say it may happen in parallel, otherwise not. And so here's an example. So if we take S3 and S6, I believe, the least common ancestor is F1, the root, and the child of that is, that's an ancestor of S3 is A1, it's an async. So we conclude that they can run in parallel. And it's true because these asyncs would have been launched, and by the time you came to S6, there's no guarantee that these asyncs with S3 would have completed. On the other hand, if we go with S5 and S6, again, the least common ancestor is F1. The child of F1, that's an ancestor of S5, is S5. And it's not an async, so we say the happens before may happen in parallel relation is false. And that's, you can see from the program, you have to complete S5 before launching the async with S6. So basically, I'm not going to get into more details. The paper has the details, but leveraging that, we kind of compared ourselves to other models. And some of the benefits we got was, first of all, reduced space overhead, unlike things like vector clocks, where the memory overhead grows with the degree of parallelism. The guarantee is per input, not per schedule. It is dynamic race detection. One key thing compared to some of the earlier work on Silk, like the SP bags algorithm and so on, is that this can be performed, this data race detection can be performed while the program is running in parallel. You don't have to serialize it. So I now want to talk about permissions. Peter yesterday had spoken about permissions more generally. I'm going to talk about a very concrete case of permissions related to read-write accesses. This is an extension to past work, of course, including Boylan's work. But we have some advances over here that were presented in this eCook paper in 2012. So the idea is that if you can annotate your code with permissions, you can guarantee avoidance, because here we are annotating and saying that in the type system that the access to the parameter, we need a write access, and the return value, we need a write access, and whereas here, sorry, not the return value, this object, that's what this is saying. That we're also going to update this object by updating the field next. And here, we'll only read this object. So it's possible to come up with a formal type system that guarantees this statically, but the problem is that that places a lot of annotation burden on the programmer. So we have a gradual type system where if the programmer did not fully annotate the program, our system can insert what we call these acquires and releases of permissions that are needed to guarantee safety for reads and writes. And what that means is when the system is introducing these, it means we need some dynamic checking. So this is all about detection of permission violations. And so we will dynamically check for permission conflicts and throw an exception and not allow the code to proceed beyond that point. And we consider these permission violations to be like bugs. That's why we throw an exception. And some other one might consider, well, if what you're trying to do is acquire a permission, why not block at that point? But we did not pursue that approach because then you're changing the semantics of the program. We're trying to detect bugs in the program, and adding blocking operations to the program will change the semantics. So the modes that we have for the permissions are shared read-only or private read-write, and that relates to the fractional permission also, because shared means it could be shared by, the permission could be shared by multiple readers. And the private read-write is per specific task, of course. So really the mode is, it's private read-write in task 1 or by task 2 and so on. And the private read-write is like an exclusive permission, and as you heard before, we can have the fractional permission, which is shared read, and could be shared by multiple tasks. So what we've shown in our work is the gradual type system gives you a trade-off between dynamic checking and user effort for annotations. So if you, in the spectrum between user effort and dynamic checks, one is if the user does 0 effort, all the checks would be inserted dynamically. And we've done some work to show that the overhead here is not that high. It can be about just 50%. And it turns out it's interesting because the granularity of a permission region is larger than a single read or write. The overhead is less than data race detection. You only have to do the checks on entry and exit. But other than that, the checking is quite similar to that of data race detection. On the other hand, we have a formal type system. So if the programmer puts more and more effort, they can reach a point where it's all statically proven. And that might be helpful not only for performance reasons, but they might be writing some critical codes where they want the static guarantee. And we've shown in our ECOOP 2012 paper that the annotation, the number, in terms of lines of code, the annotation burden is quite low. We compared it with some other projects like deterministic parallel Java, which had a higher annotation overhead. Now, I want to follow up a little bit on what Martin said yesterday. So we've taken this one step further for determinism checking as well. And so here's kind of the motivation. There are two sorts of code that people might want to verify. There's the really tricky code, which are the high-performance libraries, the internals of non-blocking algorithms, and there you may need a whole PhD dissertation to prove that one concurrent link queue is correct or another concurrent data structure. But that's not really used by mainstream. That kind of code is not really written by mainstream application developers. It's really written by concurrency experts. On the other hand, you have, I think, what are really intended to be deterministic application code, where they use the libraries in a deterministic way. So while there may be non-determinism inside the libraries, most clients of the library have a deterministic view of their parallel program. So we want to focus on deterministic checking over here and just take for granted over here, at least in our work, that the concurrency experts got the libraries correct. So yeah, this is echoing what Martin said yesterday, is that when you're in this situation, the approach is determinism checking via commutativity. So what we need to do is we need a specification as to which pairs of library operations can commute with each other. And for our work, we just trust and believe that that specification is correct. And then we can do dynamic checking of the application code to see if those commutativity assertions are obeyed. And if, just like in the, and it turns out this approach uses the same dynamic program structure tree as we did for data race detection. So if we find that two conflicting non-commuting operations could possibly run in parallel, then we will throw a runtime error exception. So here's an example. So if you have a count field with an atomic integer by itself internally might be non-deterministic, and there are certain uses of the atomic integer that could be non-deterministic. For example, if we did a get in the middle of the increments, it could be non-deterministic as to which iteration got which get. But if we do the get not in parallel with the increments, then the result is deterministic. And the finished scope in this example ensures that you get a deterministic answer over here. So specifying commutativity, we just need some kind of annotations on the methods in the library, what we call commutativity sets. And for instance, saying this read means that a get can commute with itself. These modify annotations say that the increment and decrement commute with themselves and each other. This init value is something that can commute with anything, and something like increment and get commutes with nothing. So this is the specification that our checker will take as input. And I don't have the details in the interest of time, but we basically use the same algorithm that I showed you from dynamic data race detection to do this kind of checking. And the overhead was only about like 25% runtime overhead. Okay, I need to start wrapping up. So let me talk a little bit about repair. So, you know, we spoke about avoidance, which is the ideal, but in general programs, sometimes you have to rely on detection. Once you've detected a bug, it would be really helpful to the programmer if you can suggest ways of fixing the bug. So that's a repair. And so I'll just talk briefly about our work that was presented last year at PLDI. So here's the view in our, one view of what happens in practice. Programmer starts with a sequential program, identifies two things that can run in parallel, then finds that the results don't match. They add some synchronization. They get some poor parallel performance. They remove some of the synchronization they add. Then they get data race. So this loop can go on and on. First debug it for correctness, then try to improve the performance, then again debug for correctness, and so on. Instead, we would like to follow another approach where you have, in this case, a sequential program, and the programmer has some intuition algorithmically about what might logically run in parallel. But so they say, okay, these are candidates for parallelism. It's like a draft program. Say, okay, this subcomputation, I think it should run in parallel, and so with others. But I don't want to figure out where to put the synchronization to make it correct. I'm just telling you things that are good candidate for parallelism. And the repair, and you can think of it as synthesis also because it's inserting synchronization. This tool, the goal is that it'll insert all the synchronization so as to get the programmer's intuition about what's parallelism, but also get something that's correct. Now, of course, this is very, very challenging. So our approach is right now more modest. It's just test-driven. Ideally, you'd like to find a way where you can statically verify the repaired program. So in the test-driven approach, the idea is that the programmer provides a bunch of test inputs, and that's usually available as part of their standard software engineering process. And we will iterate through them, add synchronization, and guarantee that for those test inputs, there'll be data race freedom for the repaired program. Oh, one thing I forgot to mention is that in our problem statement, we also want to maximize the available parallelism after repair, because it's one way to repair the program is just make it a sequential program. So, okay, so the overview of our approach is that we use the dynamic program structure tree to figure out where to insert finishes, but there's a close coupling with the static program. So if we do a repair in the dynamic tree, we have to propagate it to the static, which in turn might propagate to multiple instances of that construct in dynamic. And so here's an example of the coupling. So for example, in the dynamic tree, we say we want to insert a finish over here. And based on what we see in the dynamic execution statement S1, we say, OK, the finish goes here in the code. But it could be there could be multiple loops or procedure calls to this code. And there were 2 instances of S1 in the dynamic tree, so we'd have to propagate that finish everywhere in the dynamic tree corresponding to the static code. And here's an example, quick sort. So let's say the programmer's intuition is that the 2 recursive calls can go in parallel. Actually, to do quick sort well, you also need to parallelize the partition phase, but I'll just talk about the divide and conquer. So that's true, and the programmer says, that's it. I'm giving you this intuition, you figure out how to synchronize. So there is a data race, because the reason you're sorting is because you're going to read the sorted array after the call to quick sort. And you could put finishes around each async that make it a sequential program. So that's correct, but that's too much synchronization. This is a natural one. You can put it around both asyncs. But it turns out it's more than what's needed, because you're not, these are like tail recursive parallel calls to quick sort. You're not looking at, it's not like merge sort where you do the recursion, the divide first and then merge the results. So it turns out that one finish construct around the root call is sufficient to repair this program. And that's the best placement. And I tried this out on the students in my class, because that's their very first programming assignment, is to parallelize quicksort. And when we looked at that time 59 student submissions, there were 5 submissions with data races. Even though we gave them a data race checker, they still submitted a program with data races. If they had run the data race checker, they wouldn't have. And we told them, don't submit a program with data races. 29 submissions were over-synchronized, and 25 matched the output. So it shows that the repair tool could have helped these 34 students. So just to wrap up, there are a number of other related topics in our group that I haven't had time to get into: determinism checking, determinism reductions, some really interesting work with Jack Dennis on trying to define functional and structural determinism. Then getting to more concurrency, delegated isolation is our way of doing nested transactions. Object-based isolation is a way of doing extending isolated, but on a per object basis, kind of like the Java synchronized statement, but while still guaranteeing deadlock avoidance. Integrating actors. In a collaboration with Eric Mercer from BYU, we've extended the Java Pathfinder to do some model checking using gradual permissions, and just restricting the branching in the model checking to the entrance and exit from permission regions greatly speeds up the model checking. So that's helpful. And then the compiler work I alluded to earlier, that we've been looking at how using these structures to more effectively do analysis and transformations of parallel programs. So with that, let me end. I think there are lots of new challenges in parallel software, and I've tried to classify them in terms of avoidance, detection, and repair, and to make the case that these structured parallel primitives can really help provide a foundation for addressing these challenges. There's still a lot more work to be done, and these are our early experiences with some of these structured parallel primitives. So with that, I'll end and welcome questions. Yes, Akash, yeah.
So what do you think about TPL and async await support?
In the task parallel, yeah. I have to refresh my memory. About 5 years ago when we were starting, we were very closely interacting with the TPM folks. So does the async await have?
Async await is more recent than TPL.
Okay.
But it builds on TPL. So it was released in C# 5.0.
So what we call async await, I don't know if it's the same, is more like an event-driven task. That you have a task, and you have some future objects that you wait for, and then that task, when you create it, it's not ready to execute till the preconditions are satisfied. Is that what you meant?
I don't know about preconditions, but
I mean,
an
yeah,
async procedure is something that runs in the background.
Yeah.
When you fire and await, it kind of unwinds the stack and waits on the other guy and blah, blah.
Oh, is it a bit like future get, that await? I'm trying to remember.
I don't know
which
future get.
yeah,
Maybe we
okay.
can talk about it.
Yeah, we can talk. So I think we can find if we talk a little more offline and understand where it fits, I believe it will fall in that category of data race freedom implying determinism, which is very useful.
Right, because I know, talking to some people in Microsoft, as soon as they came up with this async await, it was a big hit, and everyone loves it.
Okay, so it probably is because
you don't have to do tpl.start task or wait, await. It was just very structured.
Right, so it sounds, so exactly. It seems to be very much in the structured task parallelism model. And so I think there are opportunities for some of these verification tools also to work more effectively with the structured parallelism. Yep.
If I understand well what you do, you observe dynamically problem and then you solve them by changing the source. And so this introduces extra constraints.
Yes.
I was thinking to an alternative which would be to remain more dynamic using some kind of scheduler or thing like that. That is synchronization by enforcing scheduling. Have you?
I see what you mean. Yes, that's an interesting. So if you want to, so our focus was more on repairing the program, but I think what you're talking about is repairing the execution. Yes. And I think there are application areas where that may be important. But certainly, if it's mission critical, you don't have the time to repair the program. You want to make sure that execution. So we haven't done work, but I can see how these properties could help a scheduler in that direction. Yeah.
So if we go back to the bug detection thing, what do you actually return to the developers? Do you try to return the root cause, something close to root cause, or something conservative?
So it depends. I had 3 examples in bug detection. So first was race detection. So there we return the standard thing, the 2 racing memory accesses with all their source code location and their calling context and the stack trace and all of that. For the permission violation, there we kind of return the objects for which we were supposed to have some exclusive permission, and the parallel program somehow is trying to perform the accesses in a way that don't obey the permission properties. So there you also get the permission object and the associated permission. So it's a little bit like in data race, you identify the memory location and read write. In permission violation, instead of the memory location, you have the object on which you have the permission properties. But that's also dynamic. And in the commutativity checking, it would be the 2 interfering API calls. So that's, but in a way, they're all similar. It's the same pattern. It's just from a programmer's point of view, I think it gets more and more helpful as the value is at a higher level, like the API calls, rather than memory location. Yeah.
And the second question, if I may, the last part with synthesis, have you also compared with, you say you find a good placement for synchronization such that you maximize the parallelization of the program. Have you compared that to what a compiler does?
Right, so that's interesting because, okay, so this is a very interesting topic for many reasons. So, of course, one approach, if the compilers are really good, you say give the compilers a sequential program and it figures out the path. So here, and in some sense, compiler data race detection analysis is analogous to the compiler dependence analysis in a sequential program. So they're very similar if you can't do one. So I think haven't compared it to what a compiler could do, but we've compared it to best practices for parallel versions of those programs. Yeah. Yeah. Yeah.